Inside a data center, network engineers rarely rely on a single point of failure. To ensure a continuous connection between switches, we install parallel cables. But the protection mechanism, spanning tree protocol, views redundant cables as a threat. Because traffic can loop indefinitely, it sees parallel links as a broadcast storm. To protect the network, spanning tree selects one physical cable and shuts it down, leaving it idle. The network is safe from loops, but the cost is severe. You pay for dual hardware and run dual cables, yet you only receive half of the potential bandwidth. Using LACP, we envelop the cables in an ether channel. This logical illusion tricks spanning tree into seeing multiple physical lines as one unified link. We gain combined raw bandwidth. Plus, if a wire snaps, data seamlessly shifts to the remaining line, keeping the connection up. To execute this in a lab, you need terminal access to two separate switches, connected by two cables plugged into ports Gigabit Ethernet 0/1 and 0/2 on both sides. By wrapping physical wires inside a logical container, we bypass the hardware limits of spanning tree and extract the maximum possible efficiency from our infrastructure. Before typing a single command into the terminal, you must verify the physical state of your ports. EtherChannel requires absolute consistency. Every physical port added to the bundle must be perfectly identical. This comparison shows the configuration logic required to form a bundle. Notice how the speed, the duplex settings, and the switch port mode are perfectly matched. These parameters must be identical across every member link. If you attempt to bundle an access port with a trunk port, or if you allow different VLANs on different links, the protocol will refuse to form the channel. The entire logical link will fail. You cannot engineer a unified logical connection on top of mismatched physical hardware. Let's log into the terminal of switch 1 and begin manipulating the physical ports. To guarantee our configurations are perfectly matched, we select the target interfaces simultaneously. Using the interface range command lets us apply our commands to both Gigabit Ethernet 0/1 and 0/2 at the exact same time. Because this specific connection needs to carry multiple VLANs between the switches, we configure these grouped physical interfaces as trunk ports. Now we initiate the LACP bundle. We assign these interfaces to channel group 1 and specifically declare the mode as active. The active parameter dictates the behavior of the switch. It tells the hardware to aggressively send out LACP packets and actively attempt to negotiate a bundle with the device on the other end of the cable. At this stage, many engineers close the terminal, assuming the job is done. But configuring the physical wires is only half the process. The logical container itself still needs instructions. You must enter the configuration for the newly created logical interface. Type interface port channel 1, and then configure it to match the physical links using switch port mode trunk. The physical cables are now fully subordinated to this new logical master interface. The circuit is incomplete until the other side mirrors the first. Moving to switch 2, we execute the exact same commands. Select the physical range, set trunk mode, assign channel group 1 to active, and configure the logical port channel interface as a trunk. The successful formation of this link depends on the LACP handshake. We set both sides to active, meaning both switches are constantly initiating the connection. The other option is passive, meaning the switch will only form a bundle if it is asked to do so by the other side. If you configure both switch 1 and switch 2 as passive, you create a deadlock. The connection stalls permanently because both sides are quietly waiting for an invitation that neither will ever send. A stable logical link requires both matching hardware settings and a negotiation protocol that actively demands a connection. In network engineering, assumptions lead to outages. Once you finish configuring, you must verify the results. Run Show EtherChannel Summary to drop an output table detailing our bundle's health. Look for SU, S for Layer 2, U for up and in use. Finally, ensure the physical interfaces show P, proving they are actively bundled inside the port channel. When you generate the SU and P flags on your terminal, you have hard mathematical proof that your logical link is active. By combining the physical wires into a logical channel, we solved our initial conflict. Spanning tree now looks at those two cables, sees only one massive path, and leaves all ports open for maximum data flow. This exact same logic scales to other bottlenecks. If you have a high-demand server equipped with multiple network cards, You can configure those ports as access links and lock them together, delivering heavy traffic to the server without interruption. If your terminal outputs did not match the correct flags, check out our dedicated troubleshooting video to track down the misconfiguration. Mastering logical interfaces like LACP is what separates operators who accept hardware limitations from architects who rewrite them.